Hello, everyone, and welcome to the chemistry assignment of extra credit. I'm Julian Pagnotta, and I'm just going to jump right into it. So first, we're going to look at the NMR spec of ethanol. And then we're just going to run through this list real quick, describing and talking about each one of these. So first of all, the number of signals in ethanol is 3. That's because there's 3 different hydrogens in this environment. These 3 different hydrogens are CH3, CH2, and OH, which comprises the molecular structure of ethanol. And essentially, each of these 3 different hydrogens lives in a different environment to the next. So just to take a sneak peek at what's going to happen, the OH group here, the CH2 group here, and finally the CH3 group around here. Now, we're going to dive a little bit into the position of each of these signals and kind of the theory behind how that happens. So first, before we really know about the position of the signals, we have to actually first know about the downfield and upfield. So downfield essentially just means on the left side of this graph here, the ethanol NMR, and upfield means on the right side. So as we can see, even though it's a little bit confusing over here on the more downfield side of the graph, because you have all these peaks right next to each other, you can see it's 1H, 2H, and 3H, which means that there's 3 distinct signals within this NMR. So let's look at each of these signals and determine their positions. So the first one is downfield, and we're starting from left to right, like reading a book right now. And that's this little peak over here with the 1H right up next to it. We'll get into what that talks about a little bit later in this video. But for first of all, that's around, well, it's around 3.6, 3.7-ish peak. And I already spoiled what that is before. It's the OH group. But this is more downfield because of electronegativity, right? So essentially how HMR works is it looks at the electronegativity of each hydrogen atom, and if they're near more electronegative groups, or if there's less shielding of the H groups, then they're going to be more downfield. We're going to talk about shielding and deshielding in just a second. But first, let's go over the exact values of each of these. The next value is around 3.5, 3.6, and that's these little peaks right here, the 2H. Now, this is the CH2 group in ethanol, which is between the OH and CH3 group. And essentially how this group works is it is not as shielded as the CH3 group. Once again, we'll talk about that in just a second, but it is also not too unshielded as well. So that's essentially why it's downfield. Next, we're going to go on to the third peak over here, and the biggest one, which is nice, the CH3 group in ethanol. Essentially what this CH3 group is it's around 1.1 ppm, and this group is more shielded than the other two. So now let's finally get into what shielding and deshielding is. So essentially, each atom or bond or anything like that has hydrogens around it. Well, not everything, but most of them have hydrogens around it, and these hydrogens essentially create like electromagnetic interferences. So when something is going into the NMR spec machine, these hydrogens will actually create not a reflux, but it's like a bounce back, like a pushback against the original wave and how the NMR spec works. Now, this essentially means that when, say, the wave is hitting, let's go with CH3 as an example in this spec. When it's hitting CH3, CH3 has 3 distinct hydrogens around it, and it's also bonded to all this other stuff in ethanol. But those 3 distinct hydrogens each have their own electromagnetic field. And these electromagnetic fields essentially push back on the wave that is hitting them. And this creates less interference, so it's going to make less of a wave. So essentially, the parts per million are going to be more upfield instead of downfield, because the H groups around the CH3 are creating resistance. And this resistance is actually how you see the different peaks, different groups on the NMR, and it's how you discover the locations in different molecules. For example, if we were looking at, say, the CH2 group over here, or the OH group compared to the CH2 group, we would say, oh, the OH group is next to a very electronegative, sorry, the hydrogen is really next to an electronegative oxygen, right? And the oxygen is pulling those electrons away from that hydrogen, meaning that when the wave hits it, it's going to have much more of an impact and it's going to shoot down the spectrum, downfield, that is. And this is how you determine what's next to what, but we'll get into that in just a second. Now we're going to talk about integration of signals. Like I said before, you have 1H, 2H, and 3H. Each of these means a different thing. Essentially what these are the like amount of hydrogens in not or yeah in their group. So for example, the OH group over here has one hydrogen, OH. This one has two hydrogens, CH2, and this one 3. And you can also tell these by the amount of peaks. 2, 3, 1, 2, 3, 1. And essentially what these are you can not only determine how many hydrogens are in the molecule itself, but you can also determine the amount of hydrogens that are in the neighbor group with the n+1 rule, which is part of spin-spin coupling, but we'll get into that in just a second. So spin-spin coupling is essentially when it's essentially what NMR or an HMR are for, and it's how to find the neighboring groups of molecules. So spin-spin coupling, in this example, let's go for 2H because we have almost a double, but it's a little funky looking. But anyways, with this n plus rule is this n plus rule essentially makes it so that the neighboring group is n+1. So say you had a CH2 next to, so the CH2 is in the middle of OH and a CH3. The CH2 essentially, it will have that amount of signals of the amount of hydrogens of the neighboring groups. So say you're looking for like the signal of your CH2 is just the n+1 rule. All right. Now that we've covered the NMR of sorry, I'm blanking on that. Oh, ethanol. We're gonna go into ibuprofen, which is here. But talking about the exam, I thought it'd be a good idea to actually bring in some of the ideas from previous exams just to see how everything works in total, which I think it'd be a good overview. Since I got the problem wrong, which kind of sucks, but it is what it is. So this is essentially my exam kind of like breakdown. I'm not going to show the answer because I got it wrong. I did not think that there's a carboxylic acid in there due to the IR spec, which looks like this. Usually the carboxylic acid from examples that I've seen is more roundish, which I suppose this is like a broad peak, but I don't know. I didn't think that was the case, even though in my carbon NMR, I said that there's a carboxylic acid group. But let's talk about the HMR of this example, ibuprofen. So essentially in this example, you have your aromatic rings, which are around 7, 7 to 7, 7.5, numbers around there, which is exactly what we see in this graph here. So this 7, 7 peak, 7, 5 peak is correlating to an aromatic ring, which in the previous example, although we are not looking at the HMR of this example, if we were to look at the exam, these overtones here, all these bad boys, those represent an aromatic ring, and they're also pretty obvious, which is nice. But the next thing that was in the ibuprofen compound, which is this is what ibuprofen looks like essentially, is we know that first of all there's a carboxylic acid group. Unfortunately, which I could not pick up on before, but that's this peak over here. Yeah, that tiny little one near around 11, that is the carboxylic acid group. And essentially all the rest of these peaks are due to positioning, number one, because like the number of signals is dependent on each environments. And then number two, oops, sorry, I have a lot of tabs open. Where is it? There it is. It's also due to all these double bonds here. So double bond, double bond, which are part of the aromatic ring. But each of these are different H environments, and essentially the ones that are bonded to the carboxylic acid are going to be way more downfield. And then the ones that are bonded to the aromatic ring and double bonds are also going to be much more downfield. However, like the CH3 groups, they're all over here. CH2 groups, some of them are over here, but not as many. But everything that is on the end of the what is it called, of the ibuprofen molecule, so here and here, this one's going to have a little bit of interference from these oxygens and the aromatic ring, so it's not going to be as downfield. It's going to be more upfield, or sorry, it is going to be downfield. Sorry, vice versa. What I just said. But the CH3 groups are going to be more shielded, meaning that they're going to be more upfield, while the deshielded H groups are going to be more downfield. And that's how you determine the structure of carboxylic acid, or sorry, not carboxylic acid, of ibuprofen from the NMR, as well as ethanol. I'm just going to do a quick review of all the other groups because I think it's fun, even though it is a little tricky. But if we were looking at, say, the what's it called? The IR spec, which is over here. This is nice. It's like a breakdown of it. And essentially you have your alcohol groups and carboxylic acid groups over here. We have aromatic groups over here, and also so the OH group is going to be around 30,000, or not 30,000, 3,000. And then you also have your carbonyl groups, carboxyl groups, CO right there, CO peak, which is why I ended up drawing a aldehyde. Yeah. But here's your mass spec. Now this one's useful. I definitely used a lot of the mass spec within the exam, but it doesn't help as much as the other spectrum. So I'm just actually going to skip the mass spec. HMR is what we just looked at, and then finally the carbon MR, which we dove into a little bit in here. Again, 180 points to a carboxylic acid group, not a aldehyde, but we also have evidence towards ring compounds, calculate the degree of unsaturation, and we know we have CH2 bonds next to each other and CH3 bonds on the end, which gave us this structure is what I ended up with. So just kind of a little bit different, but definitely learn from my mistakes. That being said, that is the end of our mini lesson / extra credit today. It was great talking to you guys. I'm not sure who's watching this, but Professor Ogar. But thank you so much for watching, and have a good one. All right.